Good evening, we're Group 13 and today we're presenting our work on our Deep Visual Inertial Odometry System, a neural method that estimates a robot's relative pose from synchronized camera and IMU streams. Supervised training requires data, so we use Blender to simulate a 6-degree of freedom robot outfitted with a pinhole camera and triaxial IMU, capturing images, inertial readings, and ground truth poses over 12 diverse 10-second trajectories. To mimic real sensors, we added zero mean Gaussian noise to the IMU. Data were logged at 1,000 Hz for inertials and 100 Hz for the camera, which gives us 1 camera frame per 10 IMU measurements. We evaluated 3 networks, IMU only, vision only, and visual inertial, which blends both modalities.
We score positions by mean square distance and orientation by how closely rotations line up using cosine singularity, then train every network with the Adam optimizer. A final normalization step rescales each predicted quaternion back to unit length, correcting valid rotations. Starting with relative pose prediction, just using IMU measurements, we created a model which takes input as IMU measurements for every 0.01 seconds, which make 11 measurements at 1000 Hz. The model processes the IMU sequence through 2 bidirectional LSTM blocks, for which the last column vector goes through MLP with 2 hidden layers of size 512 and 128 and predicts 7-dimensional outputs, that is relative position and quaternion. Now coming to the result, loss curve converges, and as seen in the middle image, trajectories align with ground truth on familiar paths. Yet the last image shows that the unseen trajectories exhibit drift, indicating limited generalization.
For vision only, 2 consecutive RGB frames stacked as 6 channels are passed through CNN to extract features from the images and then concatenate the feature vector, which goes through convolution and followed by MLP with hidden layers of dimensions 512 and 128 to predict relative position and quaternion. The model converges faster and generalizes better than the inertial network, though novel paths still introduce error as shown in the last image. But a hybrid model between visual and inertial sensors taps on both the cues, where images captures the large motions and the IMU redefine the subtle shifts. We use a Resonate 18 backbone and 11-step LSTM to yield visual and inertial tokens, which are fused by a transformer and a MLP to output the 7-degree of freedom pose. The hybrid network yields the lowest loss and closest trajectory traces on both training and testing trajectories, confirming that the joint sensing surpasses the single modality baselines. Thank you.